Hello everyone. I welcome you all to the Code to Discovery YouTube channel. This would be the second video of our linear regression series. Before we move ahead with building multiple linear regression models, I just want to give a quick recap of what we learned in the last video. In the last video, we talked about the importance of having models for predicting the solubilities of organic compounds. We went ahead and built a linear regression model using molecular weights of organic compounds in order to predict solubilities. Molecular weight is an important descriptor as you can expect increase in the lipophilic groups with increase in molecular weight, which in turn would decrease the solubility of organic compounds. Initially, we went ahead and used the stats model for building the linear regression model. The crucial step involved adding constant using add_constant method. Then we went ahead and used the OLS method to fit our independent and dependent variables. The results were stored in a variable called results, and the information was extracted in a tabular manner using summary method. Then we went ahead and explored Scikit-learn library, which involved creating an instance of the linear regression class. It was followed by fitting the x and y variables. R-square can be extracted from the results using score method, and intercept using intercept underscore and coefficients using coef underscore attributes. R-square value of 0.406 indicated an average fit. That meant we were missing some important information. This is in fact true as solubilities is a complex topic and is not always dependent on one variable. Therefore, in this video, we will try to build a regression model based on multiple features, and good models often require multiple regressions in order to address the higher complexity of problems. So in this video, we wanna build a multiple linear regression model with the regression equation, which looks something like that. It is similar to the simple linear equation, but it has more descriptors in it, not just one. In here, y hat is our target or dependent variable. B0 is the intercept. x1, x2 to xn are our features or independent variables. B1, B2 and Bn are the corresponding coefficients. One more point that I wanna make is, since we are gonna be using multiple features, we cannot plot solubilities against multiple features in a 2D graph. In fact, multiple linear regression is not about the best fitting line. Instead, what we want to have is a best fitting model. So without further ado, let's see how it works. Like before, I am gonna be importing various libraries which we need to build the model. The data that I'm going to be using for building the model is in the solubility_mlr Excel file. So let's go ahead and load this data and have a look at the first 5 data points. So as you can see here, the dataset has the name of the organic compounds, measured log of solubilities, and around 210 molecular descriptors which were generated using RDKit library. Now I have already made couple of videos regarding how you can generate these descriptors using RDKit. I'm also gonna be providing you the links for those videos in the notebook here, so go ahead, you can check these out. I'm also gonna be providing you the link for the original dataset from where the compound IDs, log solubility values and smile strings were extracted. So make sure you check those out. Next, if you want to have more information about this dataset, you can call a describe method. So let's go ahead and do that. So as you can see here, we have 1144 data points. mean, standard deviation, min and max values for all of these descriptors have been provided. So if you want to dig deep into that, you can have a look at this statistics. Now let's go ahead and define our dependent and independent variables. Now like in the linear regression, we just use molecular weight as our independent variable. So for this particular video, since we want to build multiple linear regression models, we need multiple features. So what I'm going to do here is I'm going to print the name of the columns. So we have the name of all the descriptors here. Next, what I'm gonna do is first define my dependent variable, which is log of solubilities. Let me just go ahead and copy the name here. So that's our target. Now for the descriptor, I'm gonna be choosing molecular weight, and I'm randomly gonna be picking up some descriptor. So let's just go ahead with Balaban J. I'm copying and pasting here. Let me store our Meyer log solubilities as a data frame rather than panda series. Now let's go ahead and run this code. So if you want to visualize, we can see Y just has the Meyer log solubilities, and X1 here has the molecular weight and Balaban J. Now if you want to get more information about it, it basically calculates Balaban's J value for a molecule. It is a molecular descriptor that quantifies the topological complexity of a molecule. It is based on graph theory and provides a measure of the branching and cyclicity of a molecule. Now in order to see if there is any relationship between this variable and our Meyer log solubilities, I'm gonna go ahead and plot a scatter plot. So what I'm gonna do here is create a figure object. Then I'm gonna add a subplot to this figure. So as you can see here, so in the first line of code, I created an figure object, and in the second line of code, I added a subplot to this figure and I stored it in a variable called ax1. Now this 2 here represents that we want 2 plots here. This represents 1, 2 here represents that we want 1 row and 2 columns, and we are gonna be adding subplot to the first index here. And if you just copy this and paste and add another subplot and index position 2, it will add another plot to the second column. And let me just store this at ax2. So now you can see we have 2 plots here. Now let's plot molecular weight versus solubilities in the first plot here, and in the second we are gonna be plotting our other descriptor. So the first one is between molecular weight and solubilities, and you can see there is a negative correlation, and we discussed that in a last video regarding this Balaban J versus log solubilities. We don't really see a clear-cut correlation. I'm just gonna leave it like that, and we are gonna be moving on to building our first multiple linear regression model using Statsmodel. Now the procedure is same here. We are gonna be adding a constant to our molecular weight and Balaban J descriptor using sm.add underscore constant, and I'm giving variable as x1. Then I'm gonna be storing the results in results variable, calling OLS, which takes in y and x, and then fitting this. Let's run this. And of course we want to see the summary. So here we have built our first multiple linear regression model. Now what I'm gonna do is zoom out a little bit, and I'm gonna be putting our results with linear regression model with just using molecular weight in here. So let's start with the coefficients. As you can see here, this is our intercept, and we see a change in the intercept as compared to the previous approach. Coefficient for molecular weight is almost same, and this is the coefficient for Balaban J. Now R square is pretty similar here. Now I want to talk a little bit about another thing which we haven't discussed so far, that is adjusted R square. We saw a little decrease in adjusted R square. Adjusted R square is a modified version of the R squared statistics that take into account the number of predictors in a regression model. While R squared measures the proportion of the variance in the dependent variable explained by the independent variables, adjusted R squares penalizes the addition of unnecessary predictors. This is the formula for adjusted R square, where it's equal to 1 minus R square multiplied by n minus 1, and in the denominator we have n minus k minus 1. Here R square is the ordinary R squared, n is the number of observations. So in here we have 1144 observations. K is the number of predictors in the model. So in this model here we are using 2 predictors. The adjusted R squared accounts for the number of predictors and adjusts the R squared value downward if additional predictors do not significantly contribute to explaining the variance in the dependent variable. It provides a more realistic assessment of the model's goodness of fit, particularly when comparing models with different number of predictors. Higher adjusted R squared values generally indicate a better fit, as they reflect a better balance between model complexity and explanatory power. So in here we have been slightly penalized for adding our other descriptor, which was Balaban J. Now in practice you should selectively choose your features. You should try to pick the best and most favorable descriptors while leaving out the rest. Also, the model is smart itself. If you pay attention to the p-values for Balaban J descriptor, you can see its value is 0.595. According to the null hypothesis, which says beta 2 is or B2 is 0, so we can reject the null hypothesis at 60% significant level. This is pretty high p-value, and for a coefficient to be statistically significant, p-value must be less than 0.05. So this variable Balaban J not only worsens the explanatory power of the model as suggested by slight decrease in the adjusted R-square values, but is also an irrelevant feature, so we should just drop this feature. So what I'm gonna do here is pick another descriptor instead of Balaban J, which would potentially have a positive influence of our model. I'm gonna go ahead with mole log P. If you go by logic, I'm gonna assume that this would have a positive impact on our model and would make it better, because RDKit's mole log P descriptor is a Wildman's Crippen log P value, and it is a measure of the lipophilicity or hydrophobicity of a chemical compound. It is calculated using a set of molecular descriptors developed by Wildman and Crippen in the context of quantitative structure-activity relationship studies. So we can assume that if there is increase or decrease in the lipophilicity of the compounds, that would certainly have a positive or negative impact on the solubilities. So what I'm gonna do here is I'm just gonna copy this descriptor's name here and I'm gonna replace it with Balaban's J. So let me paste it here and here as well. And I'm gonna run this again. Now in the scatter plot, you can see that there is a negative correlation between mole log P and log of solubilities, and that kind of suggests that with increase in lipophilicity, this log of solubilities decreases, because greater the log P value means greater the lipophilicity. So let's just go ahead and analyze our regression results. In here you can see we have an enhancement in the R square value, and adjusted R square is the same as that of R square. So that means there is no penalty for adding mole log P as an additional descriptor. These are the coefficients. The intercept of the equation is 0.1454, and a coefficient for molecular weight is this, and for mole log P is this one over here. And if you have a look at the P values for both molecular weight and mole log P are 0, that basically means both of these are relevant descriptors. So our multiple linear regression equation would look something like that, where y hat is equal to 0.1454 minus 0.0065 times x1, which is our molecular weight, minus 0.762 times x2, which is our mole log P values. Now let's just see how you can use scikit-learn for building the multiple linear regression models. Let me just zoom in a little bit. The procedure is same. We are gonna be creating an instance of the linear regression class, and then we will fit our x and y variables. We can see the R square using lr.score method. You can see this is similar to what we saw in the stats model. For intercept, just need to type the intercept underscore attribute. And for coefficients, now this time we will have two coefficients, so we are expecting two values. So these are the coefficients, first one for molecular weight and the second one for mole log P. Now of course we cannot really plot a regression line where we have solubilities versus two descriptors, but we can build a regression line between actual and predicted solubilities. So what I'm gonna do here is I'm just first gonna show you our y variable. These are the measured log solubilities. What we are gonna do here is that we are gonna generate y hat, which would be the predicted solubilities. And how can we do that? Using predict method. And the variable would be x1. So let's run this. So we have the predictive solubilities now. So what I'm gonna do here is I'm gonna use Seaborn, and I'm gonna be plotting a regression plot, which will plot the regression line as well as the scatter points between y and y hat. Here x is y, and on the y-axis I wanna plot my predicted solubilities. So here you can see we have a regression line between our measured and predicted solubilities. I'm gonna end this session right here. I'm gonna be posting more videos like that, so make sure you are subscribed to the channel. Thank you for watching.